Hi, everybody. Dr. White here to guide you through an activity to illustrate the frequentist definition of probability that you meet in our textbook. So here I am about to log into RStudio. I just provide my Georgetown College Network username and password. And I never click stay signed in when browser closes. I leave that unclicked, and I think you should too. Sign in. And we wait. And come to our own little home directory over here in the lower right-hand corner. And we've got a console over on the left-hand side. And we'd like to get to our activity. So we'll go to the ... dots here on this Files tab, ... dots. And we say / COM. COM is short for common folder. And we go take a look in the common folder and we see Dr. White stuff. We click on that. We look for a Math 331. And you'll see more and more stuff here as the semester goes on, I assume. Look at a little folder called Scripts. Go inside of it. And we see Chapter 1, Section 1.R. Well, that must be it. We click on it and it opens up here in an editor pane that got newly created for us. And we might want to change some of this, experiment with this file ourselves. So we really need to own it. And right now you're looking at a buffer that's associated with a file over in a folder that you don't have permissions to write to. So you need to say File, Save As. And you open a dialog box where you can tell you're looking in the common folder, Dr. White stuff, Math 331 scripts. So you're looking back into this area where you can't save anything. So you need to use the ... dots that you see right here. And you want to go back to your home directory, which they say is the little tilde, which is over the backtick key near the upper left of your keyboard. Here we go. Say OK. And now you're kind of pointing back into your home directory. I think I'll go into My Notes and just put it in there. So I'll double click on that and I'll just say Save. And so now this little buffer that you see in this editor pane where I'm waving my mouse, that's a buffer associated with this file in your My Notes in your home directory. You own it. You can make changes and things. Okay, let's go ahead and let's run some of the R code in this R script. So we want to attach a package that has a function that we'll be using for a little bit. And that R package is called Mosaic. So we want to run this little command right here. Now, the easiest way to run a single line of R code in R script is to just press Command and then the Enter or Return key on a Mac, Control Enter Return on Windows. You could also go and just, where you have the cursor flashing on that line, you could press the Run button here and it would do the same thing. I'm going to go ahead and use my shortcut, and I recommend that you learn shortcuts. So Command, Return, and we get a bunch of messages in the console about how package Mosaic is getting loaded. Okay, so let's go to this R flip. What we're going to do here is we're imagining a random experiment where we flip a fair coin. Okay, that'll be our random experiment. And we'd like to just repeat it once. Okay, so we say R flip once, N is 1, and we need to specify that's a fair coin. Prob is 0.5. Ready, set, go with a Command Enter. And we're flipping one coin. We got a tails. I did anyway. Your results will vary when you try this yourself. So the proportion of heads was 0 in that one try. Hey, let's flip it 100 times. So we just say R flip N is 100, huh? And run it. And so we get, some output in the console said flipping 100 coins, where the probability of heads is set at 0.5, fair coin. And here were the actual 100 results. And it goes ahead and computes up that we got 55 heads in that out of those 100 tries. So the proportion of heads is the 55 we got divided by the 100 times that we tried, 0.55. as you would expect, it's not too awfully far away from 0.50, the chance of getting a hit. Let's just like try that again. So, I could go to my R script and get on that line 8, and then you do a command enter again. But let me show you a little trick. Down in the console, if you press the up arrow, you will get the previous command that you just ran. In fact, the more times you press the little up arrow, the further back you'll go in your history of R commands. And so you can get back to stuff really fast that way if you want to repeat it. Well, anyway, I'm just going to press enter right here and try again. And this time I get 53% heads. Up arrow, try again, 45% heads. Up arrow, try again, 49% heads. Up arrow, try again, 50% heads, right bang on the nose of what I was expecting. 51% heads, 47% heads, 47% heads, 48% heads, 42% heads. And so that was kind of far away from what I expected. The proportion of heads in 100 times seems to vary a pretty decent a bit, 5% either way, roughly, on the side of 50%, but occasionally you can get outside of that, like when we got 42% heads. Well, what if we did it 10,000 times? So that's line 14 here in the R script. Let's run that. Run it. So command enter. And so it's like got a whole bunch of stuff that it has to print out here, way more than it can handle on the console. But at the end, we see that in the 10,000 tries, I got 5,030 heads. So I got heads 50.3% of the time. Let's run that again. 49.98% of the time. 50.05% of the time. 49.56% of the time. So I'm still getting variation around the expected long run of 50% of the time, but that variation is much less at a high number of repetitions of my random experiment than it was at a lower number of repetitions, the random experiment. The frequentist definition of probability says that the probability of an event should be the limit, as n goes to infinity, of the proportion of times the event occurs when you try it n times, And so you're expecting, if the probability really is 50%, then you're expecting that that limit should be 0.5. And what you're seeing here is kind of a verification of that. It seems like the more times you try the experiment, the more likely the proportion of heads you get is to be closer to the 0.5 that you were expecting. This result is called the law of large numbers. It's actually a math theorem that says that no matter what the probability of the event is, the more times you repeat the random experiment, the more likely it is that the proportion of times you got the event to occur will be closer to the probability. One nice way to see that is just like graphically. So let's go ahead and set up a random experiment again where you're flipping a coin, and let's say the chance is 0.5. I'm going to go ahead and run this line 22, command enter. And so what I've done with this little assignment operator, this less than and a dash, is that I've bound the name chance over here. See the global environment over here? I've bound the name chance to the value 0.5, so I have access to it. I can use it for later computations. And I'm also going to decide how many times to repeat the experiment before I get tired and quit. So I'll define this variable stop at here on line 24. Ready? Run it. So stop at has been bound to 500 in my global environment. And then I want to get some reusable results for a simulation of flipping this coin 500 times. And our flip isn't really going to work for us for that. It concentrates on the proportion you get at the end. and I would like to know all what happened all in between. So I'd like to preserve all my coin flips. And you can do that with a function that we'll learn more about later called rBinome, random binome. And what you say is how many times you want to repeat the random experiment of flipping a fair coin. Well, we'll do it stop at times. Size is 1 means that each time you're only flipping once. And prob is chance says that you have, a, a chance probability of, getting a heads. And what you'll actually get out of this, I'll just go ahead and run this line. You're binding the name results to the result of running that function there. And you can see over here in the global environment, it's a vector of length 500, and it's zeros and ones. Basically, R wrote in a 0 whenever it got a tails and a 1 whenever it got in heads. And so if you wanted to see all of the results, you could actually just type in results here in the console and run that. And there would be your 500 flips coded as 1 for heads and tails for zeros. Okay, what we want to do though is we want to compute the proportion of heads that we have at each repetition. So the first thing I'm going to do is count up how many heads I've got so far. So heads count here is the cum sum of results. Cum sum is short for cumulative sum. Let me run that line. And look at heads count over here in your global environment. Compare it to results. Do you notice every time you get a 1 for your results, the heads count goes up by 1? The reason is it's taking a cumulative sum of the results vector. So it's adding up all the stuff that it saw up to each point in the results vector. Okay, now if you take heads count and you divide it at each place by the right number. So what I've got here is 1 colon stop at. Let me just select that one little bit and say run. And 1 colon stop at is all the numbers from 1 up to the stop at value of 500. And what I'm planning to do is take heads count, which is this vector over here in the global environment, and divide it by that other vector of 1 to 500. And it'll go place by place. It'll divide the first place of heads count by a 1, the second place of heads count by a 2, the third place of head counts by a 3, and so on. So let's run that. And here's heads prop. Okay, let's take a little look at heads prop. Let's have a look at it here on line 32. I can just run heads prop and it'll print it out to the console down here. And we can sort of go up to the beginning. There we are. And so we got 0%, 0%, 33%. We got heads the first time after, 3 flips. And then 25% because we got a tails on the 4th try, I see in the global environment. And so, it's correctly computing the proportions, running proportions as you go along through your 500 repetitions. Now, that's a kind of hard to kind of look at there and see whether or not the proportions are really settling down towards 50%. So let me make it a little bit easier to look at. I'm going to make what's called a data frame that has 2 columns. First column is the flips, number of flips. That's the 1 colon stop at. And the second column is I'll call it proportion, and that's the heads prop vector. Let me run that line of code. I'll just get to the bottom of line 38 there at the end of that whole command. Can control enter. And now DF shows up in the global environment. Here, I can just click on DF, and it looks like an Excel spreadsheet. And so it's a lot easier there to go down to however many flips you want to go down to and check out the proportion of heads after that number of flips. And with this view, it's a little bit easier to see that the proportion of heads might be, coming closer to 50% more often. but still not as easy as I'd like. So here's a last thing. I'm going to make a graph, and the amount of this code that you like would ever have to know for this class, like in a test situation, is basically zilch. You just kind of like try it out, follow along. So try this out and follow along. We're going to run this little graphing command, the lines 39 to 42, and so I'll just get down at the end of it and run it. And I'll get myself out of the way here. Can I move myself? I don't think so, so I'm just going to remove myself instead. And you can look at this little graph that popped up. If you want, you can look at it bigger by pressing zoom. And there I am again. So let me get myself out of the way there. And what you've got here is a little graph of the proportion of heads against the number of flips so far. And there's a horizontal line at the probability of heads, 0.5. And what you see is that at the beginning, there was kind of wild variation around the 50%, but it seems that you have, kind of leveled off in your variation, although still somewhat above 50%. Let's try this again. So what we'll do is we'll just run this whole block of code from here all the way down to here again. So we'll be trying 500 flips again. Okay, so I've got all that selected and I'll press run. And we get, again, very similar behavior, a lot of variation away at the beginning and less later on. Let's try it again. And again, kind of the same general idea. Now, so you'll see that sometimes you kind of end up above the 50% by the end of the 500, and sometimes you end up below, but you always seem to end up like closer and closer. That's the law of large numbers in action. And if you wanted to, you can experiment with like a different probability of, like say the chance of heads was only 30% in this coin, and say you were going to do it 10,000 times. Let's see how things might go. I don't know if this graph will look good, but you should get something that, sure enough, after a lot of variation, comes out really, really close to the 30% long run. So I encourage you to try out variants of this code yourself, changing the chance, changing the number of times you're willing to repeat the experiment until you get the idea of the law of large numbers yourself. It's the math theorem that backs up this frequentist definition of probability offered in the early section of our textbook. Hope this helps, and see you later.